Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 28, 2025, about 5 days ago. The striking result is that this paper shows matrix-whitening optimizers consistently beat elementwise methods like Adam, cutting final validation loss from 2.98 to 2.94 and reaching the same loss in about 66 to 83% of Adam steps, while pinpointing variance adaptation as the real engine of the gains, rather than spectral normalization. The paper is titled, What Really Matters in Matrix-Whitening Optimizers, and as we'll see later, the implications for optimizer design are quite significant. Alright, Figure 1 lays out the experimental setup that isolates optimizer effects in transformer training. The diagram shows GPT-2 base with matrix whitening applied to dense weights, while embed, output, and layer norm parameters use Adam with fixed tuning. Each optimizer receives the same initialization and data order, which controls confounders. They sweep 4 knobs per method: learning rate, weight decay, beta 1, and beta 2. Well, Figure 1 set the training controls, and Figure 2 shows how validation loss shifts when each hyperparameter moves around its tuned optimum. The curves form shallow U-shapes, which means the methods are reasonably robust because performance degrades only at the extremes. Matrix whitening methods stay below Adam across ranges, with soap and shampoo variants reaching the lowest loss. Muon and Muon remain competitive, while Adam sits higher and is more sensitive at larger learning rates. So the previous figure showed robustness across sweeps, and Table 2 compares optimizers at tuned settings. The table reports learning rates, wall time, Adam steps, and validation loss, and the results favor matrix whitening methods. SOAP achieves the strongest per step performance with validation loss near 2.94, while Adam Muon offers a strong wall clock trade-off. These methods reach equivalent loss in roughly 66 to 83% of Adam steps, which signals a clear efficiency gain. Alright, Table 2 compared tuned efficiency, and Figure 3 digs into why performance differs. The figure shows that Muon enforces spectral descent very tightly, with the max to average singular value ratio near 1, while SOAP and S+ sit around 2 to 3. The left panel quantifies that spread across training steps. The right panels show that adding more Newton-Schultz iterations for Muon or more inversions for S+, still trails the red SOAP baseline, so extra compute does not close the gap. Okay. Figure 4 shows bar charts comparing signed descent methods in gray with their variance-adapted versions in red. Adam beats Signum, SOAP beats S+, and Muon beats Muon, with gaps large enough to rival the overall advantage of matrix whitening seen before. Variance adaptation means scaling each update by the square root of its historical variance, which acts like a signal-to-noise-based trust region. That adaptive scaling explains why Muon and SOAP land at the lowest validation loss. So, the previous figure contrasted signed and variance-adapted updates, and Table 3 now quantifies that pattern across 3 optimizer families. The table shows consistent gains for variance adaptation, while the lookahead trick alone did not help. Factorized variance closely matches full buffers, landing near 2.95 validation loss in the shampoo and Newton-Schultz groups, which matters because factorization cuts memory from quadratic toward linear scales. Wall time overhead stayed modest, about 1.2 at most. Wrapping up, 2 takeaways stand out. Matrix whitening optimizers reliably beat elementwise methods like Adam, and variance adaptation, the signal-to-noise-based scaling of updates, drives much of the gain beyond spectral normalization. A practical implication is modular design. Combine spectral transforms with low-rank variance estimators to cut memory while keeping performance. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.